Okay, so today we're going to talk about data analysis and graphing. Now, again, data, if you remember from the last video, is information collected from an experiment which can be analyzed and used to draw conclusions or to figure something out. And there's 3 steps when you are dealing with data going from raw data to the graph. Step 1 is collecting your data, right? Getting all those numbers that we don't want to look at by themselves. Then we take those numbers and we analyze them using either Excel numbers or a scientific calculator. And then we have our results and we can graph our data into a meaningful picture that hopefully reveals trends for us to see and maybe make predictions using. So step 1, getting your raw data. Now when you get all those numbers, there's 2 things you want to be careful of for a good science experiment. You want to make sure first that your data is unbiased. Now what that means is that the data you gather and the individuals you gather them from represent as much of the true population as possible. So that means that you're not just sampling guys, you're not just sampling girls, you're not just sampling one race or ethnicity or religion, you're getting everybody because we want a real true picture of the human population. Second standard is to be sufficient in how many data points you get, how many people you measure, how many trials you run. And so we want that because the more data you have, the more data points, the more reliable your results are going to be. When in doubt, start with 30 samples. That is a good standard to start with for statistical analysis. So getting into that analysis, the first thing you're going to do with your data is you're going to get the average or the mean. Now, an average or mean is simply when you take your data points for a certain treatment, you add up the numbers and you divide that sum by how many data points you had. So if we're looking at the heights of 16-year-old males, I've got 5 data points. That's not enough. But just for math purposes, we're only going to use 5, but you should have at least 30. So we're going to add up the heights, 5.5, 6, 5, 5.7, and 5 again. That's going to give us a large number. We're going to divide that number by 5 because we have 5 data points. And that's going to give us an average or a mean of 5.44. Now, I have this reliability range that I made up. If you only have 1 or a few data points like we do, we only have 5, then our average, our mean, is not really reliable. To be more reliable, we would have more data points. And again, if you have 30 or more, then you're on the good side, which is very reliable. So you have your mean. The next thing we have to do is analyze the mean. And we do that first by looking at what's called the standard deviation. And standard deviation is simply the variation of spread of your data around the mean. So we say, okay, here's the mean, and our individual data points range from here to here. A normal data curve would look like a bell, and in the picture it looks like the blue bell, the blue line, where most of your data is pretty close around that mean, with only a few outliers at each, or extremes at each end. If you have a large standard deviation, that's going to look like the green line, where you have a very low hill that's very wide. So you have way more extremes and not as many data points around the average. And the other possibility is that you have a small standard deviation, and that's going to look like the red graph, where you have a very tall peak with very narrow sides. In that case, you're going to have very, very few outliers. Everybody's kind of around the mean. So you can measure how good you were at sampling, because again, a good sample should give you about a blue curve, the normal. And we do need this number, the standard deviation, so we can calculate what we're getting to, which is the standard error bar, which is going to give you another nice picture. So to get the standard error bars, well, why we want it? We want it because this is how we're going to know if our average is reliable. Another way we can know. So we want to know how precise our average is to the larger population. In this case, this is going to be our sample population. So if you have what's called a short standard error bar, your mean is reliable. It means that you said the average is here, the error is somewhere to here, That's pretty close. So the real mean in your population is somewhere in here. Now, if you have a large standard error bar, pretend it goes from here to here, here's the average you calculated, here's the upper of your bar, here's the lower. That's a really big range of where your average actually is. That's not good. We want to be pretty precise in our measurements. And once you graph these, when you look at them, you'll have your average bars, like you do in the picture with the blue bars, and your two I bars, which are standard error bars. If they could be moved along the horizontal and they overlap, that means that those two averages are not really different. They're the same. Now, if those two I bars can be moved across and they don't overlap, that means that your averages are truly different. And that's going to be very helpful when you analyze a graph. Okay, so how do we calculate this without losing our minds? Again, you can do this in Excel, you can do this in numbers, or you can do this with a scientific calculator. I'm going to show you the formulas for doing it in Excel and in numbers. So, we open a new Excel sheet. In our column A, we put our data. In this case, I have my raw data for 16-year-old heights. And I have the same numbers as before, 5 data points. The next column, I'm going to figure out my average of these numbers. Now, when you put an equal sign in an Excel cell, that says, hey, you're going to do math for me, so listen up. And then once you put in that formula, the formula goes away. So I have it written above, and then I have the result down below. So the code is equal sign, the word average, all caps, open parenthesis, and then your cell range. So in this case, we're going to use column A, second row, all the way through column A, sixth row for my data. Close parentheses, press enter, it will give you the number 5.44, which we already knew, but now you know how to make the computer do it for you. So we have that mean. We're going to analyze and get our standard deviation. Again, empty cell, enter the equal sign, put in capital ST, DEV, open parentheses, put in the same data range, A2 to A6. If you have more data, which you should, it'll be a larger range. Close parentheses. Press enter, it'll give you a number. Here we get 0.439317, blah, blah, blah. We're going to round to the nearest, the second decimal place. So we'll use 0.44. And so again, our spread of data is small, and that's because if we look at our raw data, it ranges from 5 to 6, and it doesn't really go much past that. So this standard deviation is going to say of our data set, those numbers have a small spread, but that doesn't tell us whether it's true of the population at large, right? But we know it's not because it's only a sample size of 5, and it should be 30. So now we're analyzing just our little bit of data that we got. So finally, we get our standard error. And for this, I couldn't figure out how to do in Excel, so just use a calculator, and you can go online and do Science Calculator and plug this in. So you take your standard deviation, which is in column C, 0.44, and you divide that number by the square root of our sample size, which is 5. So if you do that, you end up with 0.197. And so what that means is if you take your average, which is our 5.44, the standard error is going to be anywhere from 0.197 above to 0.197 below. And that's going to be the true range of where the actual mean is. And then you can plug in those data into your graph and create your error bar and see how accurate your averages are for your data set. Now, when you make me a graph, and we make anyone a graph, it needs a few things. Give it a descriptive title so that anyone who looks at it knows what they're looking at. Usually keep it 4 to 8 words. In the example, you're looking at scores by team per season. And we can pretend this is basketball. This can be NC State in red, Duke in blue, and ECU in purple, right? And we're using multiple data sets, so we have to have what's called a key. So we know who is State, who is Duke, who is ECU. You don't always need that, only when you have multiple data sets. The other thing that you always do have to have is a label for your y-axis. Remember, that's your dependent variable. In this case, this is the point scored. You also need to label your x-axis, which is going to be your independent variable. In this case, it's the seasons, year seasons we looked at. If you don't include one or more of those, for me, you'll get points off. So remember those. Okay, and then what kind of graph are you going to make? You've got three choices here. First can be a pie graph, which a pie graph has to add up to a meaningful whole or meaningful 100%. This is used for surveys mostly, maybe population breakdowns. So here I'm looking at favorite types of movies. And if we look at sci-fi, we've surveyed 20 people. And sci-fi, 4 people liked sci-fi the best. So what percentage of the pie is that sci-fi slice? You simply take the part you're interested in this case sci-fi, the 4, and divide it by everybody you asked, which is 20, and then you get a decimal number of 0.2. So to make that a whole number, multiply that by 100 and you get 20%. And then you just plug it in. These you saw in middle school, pretty easy. The second type of graph you can use is a line graph. Now a line graph is going to be used when you want to show a relationship over time, where you know that even though you have a data point here and then another one here, in the time that you didn't sample, you know what happened, that the data is continuous over time. And if data is not continuous over time, you probably shouldn't use this type of graph. So again, here we have points connected indicating a constant predictable change over time. Temperature, time of heating over increase in temperature, that's pretty steady. The second graph is Wonka bar sales. And so this is a school that did chocolate bar sales over class periods. And they have their standard error bars. So you can compare class period to class period and see that first and second period didn't have any real difference because their standard error bars, if you could move them, would overlap. However, first period to 7th period, their standard error bars and data points, if you could move them over, don't overlap. So they're different. They're mathematically different averages. And then of course your third choice in graphs is bar graph. A bar graph is going to be used to compare information not connected by time. Here we have a favorite fruits by students. And there's a problem with this. There's 2 versions of this data, same data, but the lower graph is made to look more impressive than the top. And the way they do this is they change the scale. Excuse me, the top graph goes up by 20s, the bottom graph goes up by 10. And so be careful of someone trying to make their data look more impressive than it is by changing the scale, because a lot of people can be tricked by that if they just glance at a graph. And that's why it's important to put in those standard error bars, because no matter how much you change that scale, if you have those standard error bars, you can say, hey, these are different, or that's not different. And so it's sort of a safe measure when you're presenting data. Okay, I know this was a lot. I hope this helps. You had practice with the Ladybird data analysis set, and you only had to graph the averages. I want you to use the tactics that I've given you. Go back and graph or calculate the standard deviation and standard error bars. Put those standard error bars back into your graph for 10 points extra credit. And if you're following along but you're not part of my class, I'll try and post that worksheet so you can practice too and see what I'm talking about. And I really hope this helps you guys to understand how to read, interpret, and handle data, because it is really important, especially when you become an adult citizen and people throw data at you all the time. It's important to know how to read it and when and how to call BS when you see it. So have a good one, and thanks for watching.